to the second tutorial on MIPS programming using MARS. In this tutorial too, we shall consider some more MIPS programs and see how they can be executed using the MARS simulator. We shall continue our discussion with the program that we have written in the tutorial 1. The program was intended to transfer some data from a register to some memory location. So as you can see, the program is divided into two sections, the .data and .text. .data section contains all the data that is required during execution of a program, and .text section contains all the instructions. Since in this case we don't need any data, we have nothing to represent here. So let's move to the .text section. The idea is to transfer some data from a register to the memory. So it is essential to identify the register and the memory location. The register that was considered was one of the general purpose registers, $T1 or $9. So it can be referenced in both ways. So the first instruction was intended to transfer some constant into the $T1 register. The second was to transfer a constant value to the $1 register. In this case, that is in the second instruction, the constant that was transferred actually meant one of the locations in the data segment of the memory. Data segment because the data that would actually be transferred is not an instruction, so it has to reside in the data segment. So obviously the instruction that was chosen was one of the locations of the data segment. So $1 was initialized with this value, and then finally the third instruction was intended to transfer the content of the $T1 register, equivalently be represented by $9. So the content of $9 would be transferred to a location pointed to by the $80 register, which is again an equivalent way of mentioning the $1 register. So this is what happened. Well, the problem with this code is that we should be careful while mentioning the values of $T1 and $1. So the reason was because we used two instructions. We used an instruction called LUI, which stands for load upper immediate, and that's one of the basic instructions of MIPS. It's a data transfer instruction. The idea was that whatever be the constant value that would be transferred to a register, the lower order 16 bits of that would actually become the higher order 16 bit of the register. So that should be one should be extra careful while mentioning the value that would actually be stored in T1. Say for example, in this instruction, if you would like to store an address such as 0x100 1 followed by 4 zeros, the number expressed in hexadecimal. So this is a 32-bit number. However, if you would like this to be stored in $1, you actually have to do it in a reverse way. That is, what you actually have to write in the instruction is 0x0000 followed by 1001, because it actually takes the lower 16 bits of this constant and puts it in as the higher order bits of 1. So this was a bit confusing. So an alternate way to perform the same thing would be to make use of some other instruction, and we do have another instruction that does the same job. So it's called LI, which says that you would like to load a register with some immediate data, and say I would like to store some immediate data called 1, and the same thing. So what you expect here is that the value of the $T1 register, that's something that is interesting here. That is, unlike the LUI where the lower order 16 bits becomes the higher order 16 bits of $T1, here it's exactly as the constant, the pattern that represents the constant. So we need not worry about the the exchange of the bits in this case. So we would go ahead with whatever we would like to represent. Same thing happens for this as well. So let's store in 1 the address which we would like to choose for storing our data. Okay, and the rest remains the same. Okay, so let's save this and let's compile. Okay, so everything works fine. Let's now execute, and something to note here before we go ahead with the execution. So let's have a look at the instructions that we have written. So as you see here, the one that is highlighted in yellow, this is the instruction that we have actually written in our program. However, an interesting thing to note is this instruction, that is li, is not a MIPS instruction. So it's a pseudo instruction, and pseudo instructions are those which are not the basic instructions of MIPS, but they are instructions which are provided by the assembler to facilitate the user in writing a code. So this li instruction is not a MIPS instruction, but a instruction provided by the assembler. So the rule is that whenever in a program the programmer uses a pseudo instruction, the assembler during the assembling process would translate that into the basic instructions of MIPS and then go over to represent that in the binary code of the instruction. So let's have a look at that. So as you see, this is the basic instruction. This is the instruction that we have written in the code, and on the left side, this instruction actually gets translated into one of the basic instructions, which is add IU. $9 is the reference to $T1, and this actually is an add instruction which adds the contents of the immediate value that we have provided, along with the contents of the 0 register, which is an all 0 pattern, 32-bit all 0 pattern, and the result is actually stored in $9. So this gets translated into this basic instruction, and after this instruction is obtained, the corresponding machine code for that, which is this, is dropped into the address, which is one of the locations of the text segment. Okay, so the same thing happens for the next instruction, which is again an li instruction where we would like to store the constant to $1, and this constant is again converted to, you see here. So this is a pseudo instruction, the li instruction, which again gets translated into a basic instruction, which is the left lower load upper immediate. As you see, this is the instruction that we have used in tutorial 1. So even if we use instruction where we have mentioned the address in a standard way, it actually gets translated into the basic instruction of MIPS. And have a look at the constant that has been mentioned. It's actually reverse, because LUI prefers to store the lower order 16 bits as a higher order bits of the register. Okay, then there's an OR operation, and finally we have the store word instruction, and these are the corresponding address, binary pattern or the codes for each of this instruction, and they are stored in this address locations. Okay, so once we are done, let's proceed towards execution, and we'll do the execution in step. So the first step that we have is execution of the first instruction, that is this li instruction is over. That means we expect the value of T1 to be loaded with the value 1. Okay, so let's have a look at that, and that is exactly what is highlighted in this green. So $T1 or $9 is loaded with a value 0x00000001. Okay, so that's what happens after the first instruction. Let's execute the next step, that is the next instruction, and what we expect is to load $1 or $80 with this value. Okay, so let's see that, and yes, indeed, $80 is loaded with the constant, which is hexadecimal value 0x1001 followed by 4 zeros, and this actually, if stored as a constant in 80, refers to one of the address locations. Let's have a look at which is the address location this refers to. and this actually refers to the first address location of the data segment. Okay, so 80 is actually behaving as a pointer pointing to one of the locations of the data segment. Now let's execute the next one. Well, so after you execute this value here, so we have reached so let's have a look at this. Okay, so the moment you execute the last instruction and have a look at this, the one that is highlighted in blue is the value that is currently stored in this location 1001100000, and that you see is the same value as that of $T1. So this is how we can make use of these pseudo instructions to execute the code. Okay, well, so this is a nice way to show how we can transfer some data from the MIPS, one of the MIPS registers, to the one of the memory locations in the data segment of the memory. Well, the problem with this kind of an approach is that the programmer has to be aware of the exact location of the memory. Okay, so in this case, as you see, we had to be aware of what is the location where the data has to be stored, and this is pretty difficult. So, is there a better way to write the same thing without actually mentioning the specific memory location? This is the first problem. And the second is, once the program gets executed, all the visualization and debugging is done by looking up to the either the register contents here or to the contents of the memory. But it's always difficult to have this kind of an approach. So an alternate to this would be if the output could be visualized in the the message box which is displayed at the bottom. And in order to do that, what we can do is we can make use of something called the operating system. So what is that? Well, the operating system is actually a software that that sits something like you can consider the operating system to be a middleware, and this is kind of an interface between the application programs that we write and to the underlying hardware. And when I say hardware, I actually mean all the relevant hardware, which includes the CPU, the memory, the input output devices. So suppose you would like the application, which is the program that you are running, to utilize one of the hardware. Let's say the output console or the terminal that on which you would like to print the screen, for that matter. So instead of the application directly being utilizing the hardware, what it can do is it can put a request to the operating system, and so it can put a request mentioning that I would like to utilize this hardware, and the operating system in turn would access the hardware on the behalf of the application and would provide the results back to the application. So say it puts a request uh, to print something. Okay, say it would like to print to the screen. So this is the request that it puts, and the OS gets the request, does it on behalf of the application, and returns the result back to the application. Well, so how does it put the request? So the request is put through something called system calls. So these are, you can consider them to be like some functions which the OS has, OS maintains, and the application has to uh, know one of them and has to put the request. So for different system calls, we have different system called numbers. Okay, so suppose you would like to have a system call for the print. Now what you would like to print, whether you would like to print an integer or you would like to print a string So for each one of them there are specific codes. So each has a system code. So the application has to know the system code and accordingly pass on to the OS this information. So what the application would do is, so here is the application, and if the application wants to request to the OS, it has to do through a particular request message which we call syscall, and it also needs to pass the system code. Okay, and finally it wants to pass the argument. So you can assume system call like a function where you are, whenever you write some functions in a high level language, you need to invoke the function through the function name and pass on the arguments. So it's the same that happens here. This is the request that the app makes to the OS through something called the system call. Then it passes the system code, that is which is the system call that you should execute, and finally it passes the argument. So that is another way to execute. So let's say we would like to do that. Well, so in order to do this, the command that one needs to write is called syscall. So this is the way in which the program would be putting its request to the operating system. Well, so that what exactly do we need? We would need to print something. What do we print? So whatever you have to print, say you make use of the, let's say we use the sudo instruction li, and here we have a certain number of registers which can be made use of. So in this case we have a register called a0 where we would be putting a value, say an integer called 2, and so this is the argument that we would like to pass. And what is the system code? Well, so in order to pass the system code, we would make use of the register called v0. So v0 is a special register that holds the system code. So suppose you would like to print an integer, so the system code for that was 1. So this is the system code for printing an integer. Okay, so which is the integer that you would like to print? The argument is loaded into the register $a0. So all the arguments related to the a specific system call would have to be in one of the registers, the A registers. So we are making use of the register A0 in this case. Okay, so the $v0 contains a constant 1, so v0 is loaded with 1, which actually is the system code for printing an integer. A0 is loaded with the constant 2, which means A0 contains an integer 2, and then finally when we type in syscall, it actually asks the operating system to print the integer loaded in A0. Now, so let's save this and let's assemble and let's execute. Okay, so let's do it again. Let's assemble. Okay, so here you have the output, which is 2, right? And let's quickly have a look at what has happened in the registers. So the registers, the two registers that we made use of are $v0 and $a0. So $v0 is, yes, this is loaded with a value 1, which is the system code for printing an integer. A0 is loaded with the integer, which is 2, that we would like to print, and then we have asked the operating system to print this on our behalf. Okay, so this is the way in which we would like to execute any program, and this is a more easier way because you don't need to care about the address of a memory and the output, whatever you have. Okay, so in any case the execution is happening and the registers and the memory locations are obviously updated, but in order to visualize the output you don't need to go and look it up in the register set or in the memory location. So the output is generated and is displayed on the console.